Can you see the cursor I am moving on the screen? Hello?
No, sir.
No, sir.
Okay, no problem. Okay. Just see over here. In this slide, there is a discussion on flight planning. Okay. And while flight planning, what we do on the basis of the requirement from the user end, like what kind of data density the user want, and what is the objective, like what kind of objects the user want to identify in the LiDAR point cloud data, and additionally the time of operation. Okay, so to decide the various parameters, these three options are considered. Okay, so quality of the data, how detailed information is there in the data, and what is the time of data acquisition. Okay, so on this basis we decide pulse firing rate, scan rate, speed of the flying this moving platform. In case of airborne laser scanning, it's flying aircraft, while in case of UAV LiDAR, it's UAV. In case of vehicle, ground-based platform, and if it is moving, it's vehicle. Okay, so that is speed we consider, and we also consider the total field of view. Okay, and all these parameters are decided on the basis of users requirement in terms of point density, where we consider the line density along the scan line and line density across the scan line. Okay, so that derivation we have already completed. Fine. But in our discussion, we incorporated only the unidirectional scanning pattern. In this case, it's a zigzag bidirectional scanning pattern is shown. If you see in the figure, like from left end to right end, one like the swath is covered, but again from the right end only the lines come to the left end. So this bidirectional scanning pattern we obtain when we use oscillating mirror in the laser scanner unit. Is it clear to all? ये clear है सबको?
Yes, sir.
Yes, sir.
Okay, fine. So in the given assignment, aim is to derive line densities along the scan line and across the scan line for bidirectional scanning pattern as it is shown in the figure over here. Okay. So what we do, if you remember the formula for line density along the scan line, what it is? So line density along the scan line is derived as number of points per scan line. Okay, number of points per scan line divided by scan rate. Am I correct?
Yes, sir.
Okay, so this is the standard formula. Now we'll see how we define scan line over here. Okay, so number of scan total number of points per scan line divided by scan. In this case, the scan line is defined as from left end to right end again to the left end. It means one oscillation is completed and this entire length is incorporated. It is like this scan rate. Okay, So the entire point is included over here. Fine. But the n, how we calculate n over here? Sorry, this in this case, the line density along the scan line is calculated as length divided by number of point divided by length. Is it? It's not a scan rate. Scan rate we use to calculate number of points in one scan line. Okay. So how you calculate number of point in one scan line? That is equal to pulse firing rate divided by scan rate. Is it? How many points are fired in 1 second divided by how many lines are covered in 1 second. So the pulse firing rate divided by scan rate gives you the number of points in one scan line. Okay. So in this case, what it will be? The point we are talking, the point which we are getting, dividing by pulse firing rate divided by scan rate. What are those points? Are they are these the point n? So the points n, are they lie only from left end to right end? The line that connect from left end to right end, or the line that connect from left end to right and again to left?
So right to left and again left to right.
Right, left to right, right to, in this case, let's say if you start from left, then left to right, and then right to left. Okay.
Yes, sir.
So that will be capital N, and it is equal to pulse firing rate divided by scan rate. Is fine. Now, what is the length that we calculate? Now our aim is to what is the distance between two successive points that we derive dx along the scan line, dx along, and 1 by dx along will be line density along the scan line. So inverse of the distance between two successive points gives you the line density along the scan line. Okay. So the length which we calculate, that is swath. Swath is calculated. It is equal to 2h tan theta by 2. Am I correct?
Yes, sir.
Yes, sir.
So the dx, that is length, the spacing between two successive points along the scale line, that is dx along, is equal to what it will be in this case. That is total number of points in a line that starts from left end and into the right end. Because that length only we are considering 2h tan theta by 2, it's swath. So either you double the swath, okay? If you double the swath, then what it will be? It will be n divided by 4h tan theta by 2. Considering the assumptions, like rather than slant, you can consider it straight. Straight means it's intersecting perpendicular the right boundary and left boundary. So what you are doing? You are considering double of the swath. So capital N divided by 4h tan theta by 2. Okay.
Yes, sir.
Why
Yes,
we are
sir.
doing what? Correct. Why we are doing this? Because scan rate, the way we are defining this scan rate means in one scan line is considering double of the swath. Okay. So the formula, the n that we are getting, that n value is equal to pulse firing rate divided by scan rate, where pulse firing rate, it's clear, number of points fired in 1 second. But when we define the pulse, the scan rate, scan rate gives us the number of lines covered in 1 second. Now in this case, the total length which we are considering as one line is 2 times swath. Okay. So what will be the density compared to the unidirectional scanning pattern? Will it be doubled or it will be halved? Will it be half or it will be doubled?
Sir, half.
So it remains same, sir.
Half meaning is that
So it is remaining same.
if you compare with the unidirectional scanning pattern, it's bidirectional pattern and unidirectional pattern. Will it be same?
Sir,
Because
when we are calculating n, then n means number of points fired per second upon number of scan lines generated per second. So then number of scan lines generated per second, whatever we are considering, that we would take half, because if we are going left to right and right to left, then we are considering it as a one scan line, isn't it, sir?
see, f is fixed. Okay, the scan rate we are not going to change. It is there. Okay. So if f is there, but it incorporates double up the length, and it is considered it as a one scan line. Are you getting the point? So that
Okay, sir.
n value we are not going to change. That n value incorporate that total points from left to right and right to left. That is considered as one line. So in one scan line in bidirectional scanning pattern having a length double of the swath. Are you getting the point? So that is why the capital N is divided by 4h tan theta by 2. It means the spacing between two successive points in case of bidirectional scanning pattern, what it will be? उस केस में what we are doing, we are dividing it by, instead of 2, we are dividing 2 times. Okay, so that spacing is actually reduces. And if you calculate density 1 by dx, then what it will be? It will be 4h. Okay, it is fine. When we calculate, when we divide n divided by this 4h tan theta by 2. Okay, so obviously what we are calculating? We are calculating number of points per unit length. Calculate. It is fine. So it is actually density we are calculating directly. Okay, if we divide 4h tan theta by 2 divided by n, then we are talking about the spacing between two successive points. So in that case, what will happen? At the same speed, the more length is covered. Okay, so the capital N, when we divide it by 2 times, in case of unidirectional scanning pattern, it is 2h tan theta by 2, while bidirectional it becomes 2 times 4h tan theta by 2. So what is happening compared to unidirectional scanning pattern? The density decreases. And why it is happening? Because the point is spreading along a line that is having double the length compared to unidirectional scanning pattern. But it is well distributed. Just see, though along the scan line, the spacing increases, but if you see the gap between two successive scan lines, okay, along the flight line, okay, so there in the middle you can see one line. Okay, it means the point density is more uniformly distributed in this case compared to the previous one. And why it is happening? reason is that the this scan rate that we consider, that scan rate is like one int to another int, then back to the previous int. Is it clear?
Yes, sir. Sir, whether it is unidirectional or bidirectional, the F scan line will be same, only as represented as F scan line.
See, the scan frequency, it is given with the instrument that we use, okay, and it is fixed. This when we talk about this scan frequency, so it is fixed. Because see,
No, sir. Means I was asking that when we are scanning in one particular direction, then we are taking a particular from left to right as a one scan line, one F scan line, and when we are doing it from left to right, then right to left, that one is completed one oscillation. Then
it's,
should we not?
yes, one, yeah, no, one oscillation include a complete, that complete oscillation is included over here, and corresponding to the complete oscillation we define the scan line.
Okay, sir.
It is not a case in like in the context of unidirectional scanning pattern, no? Because what happened, it's a rotation. So one int to another int, then it completely rotate. Though those points are fired in the sky, so they those points do not hit the ground. So that's why we exclude them. Then again there is a gap. Once it complete upward rotation, then again it comes down. So in that case, mirror direct the laser beam towards the ground within the swath theta that we consider over this field of view theta to cover the swath.
But then density across will be same as it is in the unidirectional case.
Yeah, what we do in that case, because see, density across the scan line is not easy to determine in this case. Okay, you can see that like, so what we do as the Y, you can see at one end the spacing is shown, the left end it is Y. The Y actually it's a gap between two, if you consider either right end or left end. Just see the gap between two successive points along the flight direction. Because see, if you come in the middle, then there is one line crossing that. Okay, so this is the reason why we either evaluate at left end or right end to the swath. Okay, and it will comes out to be same because F is fixed. So it comes out to be same. It will be equal to how much it will be? Scan frequency divided by speed.
Yes, sir.
Okay, and the spacing Y comes out to be speed along the flight direction divided by scan rate. So that will be distance covered per scan line. But what benefit we have in case of bidirectional scanning pattern, we have a line, additional line in middle. Okay, and due to that, we have a more uniform distribution of points. Like along the scan line, if you see, though this across the scan line, that is along the flight direction, If you see, though we calculate density at either left end or right end, but if you see in the middle, then there is one more line that is crossing, that is connecting the left end to right end. Okay, and that additional line in between two successive lines along the flight direction that we consider, that is that leads to the more uniformly distributed point cloud.